Okay, hello. I'm really happy to be here. But first, a little survey. How many of you know what FreeMonad is? Okay, so quite a lot. And how many of you used actually FreeMonad in your production code in your daily job? Okay, just a few. So I was also not using FreeMonad in my daily job since lately. So today I'm going to teach you how you can take advantage of FreeMonad in your real-life application. Okay, first a word about myself. Sorry, that's the agenda. First, I will tell a bit about myself, then I'm going to make a brief introduction to FreeMonad, but I promise it to be very brief. Then I will show you what my use case was, and then I will show you the code examples, and I will explain how using FreeMonad was good for us. Okay, so a word about myself. I'm ex-Scalar organizer, so I'm really happy to be here as a speaker. I'm a software engineer for quite a long, and currently I'm working for .data. You can catch me on Twitter and on GitHub. That's my Twitter handle and GitHub handle. And you will find all the code on my profile that would be on this presentation. Okay, so what FreeMonad is. So FreeMonad actually allows us to build a monad from the DSL that we want to define. So that's a very simplistic definition. I know that probably there is a smarter way to express it. But if you would need to remember one thing about FreeMonad, I would like it to be that you are able to build a DSL and wrap it with a monad. And in this way, you may represent your your computations as a data structure. Okay, so first the DSL. This example is taken from type level page, and you probably have seen it if you were trying to learn what the FreeMonad is. And actually, that's a DSL for key value store. So here we have 3 different operations. And as you can see, the base trait can return type A, but not all operations are returning something. For example, delete or put, they are returning units, so they are not passing over any other things to the rest of the program. And actually, get operation does, it returns option from T. Having this DSL, we are able to write a program which is very clean and neat. You don't see any technical details here. You don't see any Spark session hanging around or transactions. It's a pure domain code, and it's beautiful. And you can also see what would be result of this program. So the result would be option of end. Okay, I cheated a bit because to write this program, you need also FreeMonad, not only your DSL. So FreeMonad is actually a kind of a glue that allows us to wrap around our DSL to write a program like that. Okay, so that was a brief introduction to FreeMonad. So right now we can go to the use case that we applied it for. So those are the pipelines for AI/machine learning. So I'm working for .data, which builds a product that is advertised as feature discovery platform. Actually, what this product does, it finds insights in data, and those insights are called features. And features are used to train machine learning models. So feature in machine learning field have different meaning. It means the measurable property or characteristic of a phenomenon, which I would translate as a number that we can calculate for a thing that we want to calculate a prediction for. So that's a number. For example, this is the Titanic competition on Kaggle. Probably most of you heard about it because it's like hello world in the data science world. So in the Titanic use case, we need to predict if somebody will survive catastrophe or not. And we have 1 row per passenger, and we have some data here. So we can say that the age, for example, is a feature, because that's a number, and we can take this number and fed it to the machine learning algorithm, and we'll get some model. based on it. But for example, sex, it's a string. So if you would like to use it, we would need to encode it as 0 and 1s, for example. So that would be a feature engineering. That would be creating a feature out of a column. This is a very simplistic approach, but that was the simple example. Here we have more complicated examples, so we can have like one-to-many join between our target row that we want to make predictions for, or we want to learn our model. And we have a transactional table. So the feature will look like in this example. So that could be a sum of transaction amount in the past week. So we can express this feature as map, filter, and reduce operations. But why transactional amount? Why 1 week? Why sum? Why not mean? And so on. So what our product does is actually browse a huge space, counted in millions of combinations, and find the best features. Okay, so let's get down to pipelines. So we have two kinds of pipelines in our product. So first is the training pipeline or discovery pipeline. And our product is a general usage product, so we don't know what data set our user has. It could be like one big flat table, or that could be many small tables. There could be many joins between those tables. And also user provides the metadata that are descripting the data. And then first we need to clean those data because it could be dirty. And in data science, they say garbage in, garbage out. So we need to remove duplicates. We need to check if the columns are containing proper values, or maybe some column was declared as string, but it's actually a date, and so on. And we need to prepare the data for the next stage to be easily digestible by it. So the next stage is the feature engineering. So we are exploring this huge space of features that I have told you about, and we are picking the best one. And at the end, we are training hundreds of machine learning models, and we are picking the best with different hyperparameters, and they are fed with those features that we have calculated, and we are selecting the best machine learning models. So at the end of this pipeline, user gets recipe how to prepare the data, how to calculate the features, so those filter map reduces that I have told you about, and we have the machine learning models at the end that could be used to make a prediction. Okay, so the other kind of data pipeline that we have is the prediction pipeline. So here we are also providing the data set with its description, but we don't need to explore and find out what those data are, and we don't need to profile those data anymore. We already know how to prepare the data because we learned it during the training pipeline, and we need to how to produce features because we have the recipes for them, and we have models trained, so we can just pass the value of those features to machine learning models and get prediction results. So we have those two kinds of pipelines, and they are very different. Because the first one can take really, really long, because we need to explore, we need to find out what those data are, how we should process them, what the features are, what machine learning models are the best, and so on. So this is a really complicated and complex pipeline, and it may take days, hours, or even days in some cases. But the prediction pipeline should be really fast, because we already know what we need to do, and we want to give our customers number, for example, if this passenger will survive the catastrophe or not, or how many soda he should order to his stores as fast as we can. Okay, so how to apply a FreeMonad to this use case? I have a sandboxed project that I have extracted some code from our pipelines and simplified it a bit for the purpose of the presentation. And I will focus on those first stages in the pipeline processing. So I will focus on profiling, cleaning, and preparing the data during the training pipeline, and then we would need to make it again according to the recipes that we know before for prediction. So we call this stage in this bigger pipeline preprocessing. Okay, so what's the data model? I already said, actually, the user is providing the data set, so it's a set of tables, and provides the metadata that describe this set of tables. What columns we have, what tables we have, what are the relations, what is the target table, what's the target column, and so on. And our DSL is really simple. It contains just two kinds of operations. First is profiler. So profiler actually takes the data and metadata, do some calculations, and return a data profile which is described as this A in the type definition. And transformer doesn't return anything to the rest of the program. It just takes the state and updates the state according to the recipe or the implementation of the particular transformer. Okay, so show me the code. That's my favorite part. Okay, so let's go to IntelliJ. Okay, so first let's start with the domain and DSL. As I've just showed you, we have the definition of the pipeline stage, and we have two kinds of operations. We have profiler and we have transformer. So profiler can return data profile, transformer doesn't return anything, and we have also a third type, which is called get metadata. It just takes the metadata out of the state of our pipeline. And here we have examples of the actual profilers that we have in our pipeline. This is just a subset, of course, of the true ones. So we have null ratio calculator. So what it simply does, it's calculating the null ratio per each column in table and returns the map of those values. And we have date column detector that detects date columns that were declared otherwise. That's the profiler. And it returns the set of those columns. And we have date column transformer. So it just simply take as an input list of the columns for a table that actually are date columns and transform them to be date columns. Okay, so let's see how to write a program using that. So here we have our program. And what we need to start is the plan for our pipeline. So let's see how the plan looks like. So that's the plan for all tables. So first we get the metadata for whole data set. Then we are iterating over it. And for each table, we are calling the sub-pipeline, let's say. And in this pipeline, we are first profiling to detect the date columns. Then, if date columns were detected, we are transforming those columns to be date columns. And at the end, we are calculating null ratio for each column and returning it to the program. And we end up with the table profile. And all the table profiles are being assembled as the data profile. Okay, so let's go back. Okay, so we know that we have a program, and this program will return data profile. And right now we need a compiler to compile this program. So here's the compiler. Okay, and when you saw the pipeline, in pipeline we had only the domain logic. We have the flow of our pipeline that we're describing what operations we want to perform. And the compiler, what actually does is translating those definitions to recipe how we should execute those steps. But it does it also on some higher level because it also, besides delegating execution to the proper type class, it also encapsulates cross-cutting concerns, such preserving the state or audit log. So here we have a transformer. So for transformer, we get the current data model from the state. we are applying transformation. Then we are storing the executed stage in the audit log. And at the very end, we are updating the data model in our state. And we are not returning anything. And in the profiling mode, we are getting the data model, the current state. We are calculating the profile, and we are returning profile to the rest of the program, and we are storing the executed stage in the audit log. So in general, we see here that we don't have domain logic anymore, but we have some kind of application logic here, and the cross-cutting concerns such as preserving the state or audit log. If you would need some kind of authentication, we could use it here. And you can see here that this compiler is typed with two types. So first would be the monad that we'll use as a target monad where we translate pipeline stages to. So that could be, for example, cats.io. Or it could, and the second one is the actual data type. So here we are not bounded, for example, to in-memory data structure representing the table. Or we are not bounded to the Spark data frame. Here we have just a wildcard that we can use. And we need to provide implicits at runtime of this compiler. OK, so let's go back to our program. So we have the compiler. We are compiling our plan, and we are ending up with plan monad that returns data profile. So right now what we need is the input. So we are building some data model that contains metadata and data. And we are using just a simple type table that I defined for the purpose of this presentation that keeps the table state in memory. And then we are running our program. So let's run it. OK, so voila, that's the result. So we have the list of stages that were executed for each table. So we have the profilers and transformers. We have the updated state here. So as you can see, we had in our input, I will show you later on. We had strings that were in the date columns, and this date column was declared as a string, and it was converted to the actual date column by the date transformer. And at the very end, we also have a data profile. So the data profile is the result of our program and could be passed over to the next stages of our processing in our application. So here we are returning the null ratios for each column and each table. OK, so let's get back to our program. And right now, what we would like to do is to run the prediction pipeline. Because as I said, we have two kinds of pipelines. We have the training pipeline, and then we have a prediction pipeline. So for prediction, we need also define the data model that or the data set that we want to use and make predictions for. And here, we can, out of the execution journal that, as you recall on the output, we store all the values of the stages that were executed. So we can just take those stages and leave them to the monad. What does it mean? So we have the list of stages, and actually you are making fold left, wrapping around each transformer with FreeMonad. And actually what we also do, we are not wrapping around profilers, because during the prediction we don't need profiling anymore, because we did all the profiling during training, and the profiling was done to make decisions, not to influence on the prediction result. OK, so then we can we have our prediction plan, and we can compile it with exactly the same compiler we used for the training plan, and then we can just run it. Actually, this run part is quite ugly, but we are using state monad with writer monad and with IO monad, so we need to have those free runs actually and providing the initial data model. But at the end, we are ending up with the data model that was transformed after prediction. So I will run it. OK, voila. So we have prediction pipeline. And we have processed the data in the same way for training, except omitting the profiling stages. OK, so how we did it? Actually, I haven't showed you one thing, because to make this compiler to run, we need implicits to provide. And actually, that's the part where the whole logic is implemented. So it's implemented in the implicit. I call this object table ops, and it provides the implicits. And here I actually have the definitions of real operations that are executed. So only here I'm using the type that is defined. So here I'm using in-memory type, which is table that I have created, and I have date column detector for this type that does the detection, and I have null ratio calculator that uses this in-memory type and does calculation. And of course, I have a bit of boilerplate on the bottom, because I need to wrap around those operations with table transformers and IO monad. So I want to demonstrate one thing. I will exit from the presentation mode for a second. So if you will have a look how the package structure look like, it's really nice, because we have, in our domain model, we have just the data model and the definition of our pipeline. And that's all. Then we have a compiler in the application package, and we are just using the domain, and we are defining how we'll translate the DSL to executable recipe, let's say. And here, that's the only place when we have the cross-cutting concerns as audit log or preserving the state. So the code is really clean. And at the very end, we have infrastructure package that we have the implicits for in-memory calculation. So I really enjoy that order, and I'm happy with it, because thanks to that we have clean dependencies. And if I would need to change the pipeline or maintain the pipeline, I don't need to focus on technical details, on cross-cutting concerns, because they are defined somewhere else. Here I have just the definition of my pipeline, and in the compiler, on the other hand, I have just the cross-cutting concerns and how those stages would be executed, but not exactly how, because how is defined by those implicits, and those implicits are in the separate package. OK, so that was an example for in-memory application. So let's imagine that we want to write and run it on Spark. How difficult it would be? It wouldn't be difficult at all, because I almost copy-pasted the same code. The only part that differs is that I need the Spark session before, and when I'm creating my data types, I need to provide not that in-memory table, but Spark data frames. And I need also to provide implicits for Spark data frame. But the rest of the code is almost the same. And we can go and see how the implicits look like. So if you would have a look over here, we have the same date column detector or null ratio calculator, and we have also a bit of boilerplate, but the difference is that we are operating on the data frames. So for example, this one is maybe not the best use case because it's checking just the metadata, but here, for example, we are calculating null ratio using Spark SQL functions, not operating on in-memory structure. So let's run it. Okay. Okay, voila. So as you can see, output is almost the same, except that we are printing the tables in a different form, because that's how Spark prints the tables. But we didn't need to write any additional, we didn't need to change our program, because it already covers how the pipeline should look like, what are cross-cutting concerns. All we need to do is provide the different input, and all we need to do is to provide the implicits that will allow us to run our data pipeline on Spark. Okay, so let's sum it up. So FreeMonads led us to build a nice and clean DSL that expresses only what our program does, not how it does. So we have the separation of definition from the implementation. It also, due using compiler, we can separate our domain logic from cross-cutting concerns as preserving the state of audit log. And in our case, so in the case of my project that is actually running on production, we had also a couple benefits, because we have written no code to create the prediction pipeline, and some back in time we had to maintain like 2 very similar pipelines, and when we would change one step in one pipeline, we need to change the step in the other, and so on. We can also easily load up the result of the training pipeline, because those were just plain case classes, so we can serialize it with JSON, and we can load it, and we can lift it up to the FreeMonad and execute it again compile it again with the compiler and run it. So we can store the past executions. So that was also very important for us, because if the new prediction pipeline would differ and we would like to run some past executions, we could have some kind of incompatibility. And this is, I think, it's the best advantage in my case. So in my case, ability to run our product on different processing engines, such as Spark or Snowflake or SQLDB or in-memory database, it's actually really an edge, because we want our secret is our algorithm, how we find features, how we prepare the data, not on which platform. So we want to be robust. So we want to be able to run our pipelines on different runtimes. So that was really a thing. It was not just changing IO monad to ZIO monad or the other way. For us, it was ability to be able to run our product on different platforms. And we are also able to put cross-cutting concerns aside, which also makes maintenance of this code and extending this code much easier. Okay, so that's it. So thank you for your attention. If you have any questions, I think we have like 2 more minutes.
Minute 45. Okay, guys, do we have a question? Yes, we have a question here.
Thank you for a nice presentation. My question was about comparison of the FreeMonad approach to competing approaches. So FreeMonad is not the only way you can separate declarative parts of the program from implementation. And could you tell something? What were the unique advantages of FreeMonad over some other approaches that wouldn't bring these benefits to you?
I'm not sure what we are comparing to, so it's difficult for me to say what are the advantages of. Could you give an example?
For example, to final tagless.
To final tagless. Okay. So I think that here we had this separation with the domain model, and with the compiler that was addressing cross-cutting concerns and like storing the state, for example. And so our domain code was not littered with preserving the state or fetching the state. It was just declaring which operations we want to execute. And I'm not sure how I would implement it using tackless final. Does it answer your question? OK, so we can catch on later, maybe.
All right, so the time is up. Łukasz, thank you so much for the talk.